When we heard about the plan for this year's program, and especially thinking about how to integrate it in Foreword, it came to mind that a lot of folks don't understand the relationship between the two ways that we do leverage in the man-machine interface. They come out, classify it as artificial intelligence and machine learning. They're different, and the panelists we've got today, that you'll see, this is the first of three, do sort of highlight the differences in the way they operate between the two activities. So just for quick purposes of understanding, one of my mentors said a long time ago, definitions are very important. They change and people disagree about the wording in almost all cases. So to be very clear, when we're talking machine learning, we're talking about the use of machines to help us leverage data and solve problems we already know about. We know what questions to ask. What we don't know is how to slam all of the data into these days, there's a lot of it, into a problem to solve it. So machine learning takes large quantities of data with a question we know, and then lets the computer work through the commonalities in the data and find an answer. A lot of times that leads to new questions, but it's still driven by the human. In the case of artificial intelligence, we slam data at a computer and say, what can you tell me about this information? We don't know what questions we're asking. The computer is actually going to go through and say, I found something new here. Is this of interest? And the only human interface is yes or no. So a long time ago, an AI machine learning algorithm for image analysis discovered cats just off of all the lolcat videos and actually defined a new class. So we're trying to do this on a much broader scale. Scale is actually the whole point here. We're trying in the process of the One World Terrain program, which is what's going to be featured in this panel, to expand our understanding of geospatial data at high resolution to the whole planet. We're going to work through creating a very large map at very high resolution of the whole world and then make that the center point of something. And our panelists today are going to talk about that. With me on the stage is Zaworski from Vricon, Meida Chen from USC, and Josh is from the Army, actually just moved into the Army Geospatial Center. And you'll hear from all three of them today, perspectives of the problem. So I'm going to go ahead and move on to Isaac to start talking about the process.
Thanks, Barry. So my name is Isaac Zaworski. I'm a vice president at Vricon, and I have the pleasure of getting to work with Barry every day. So I'm not going to give him too much of a hard time about the AI definition that was presented earlier. He knows my feelings about that term in general, and I'm going to, for purposes of my own, I'm going to stick with machine learning and computer vision, neural networks, deep learning, all those different things that are somewhat easier to define. But Barry invited me to be a part of this panel to provide some context from the industry perspective in what it means to think about a problem set like what is being proposed with One World Terrain from a technology standpoint, and what industry is doing to bring some of these new capabilities to bear to address a problem that is a big problem. And the scale term is a key part of that bigness of the problem. So for those of you in the audience who are not as familiar with the term One World Terrain or the Army program that it falls under, this is a concept that has been in development and been brewing within the Army's ecosystem for several years now. And it actually comes out of an effort underneath Army Futures Command and one of the cross-functional teams that's focusing on their concept of the next generation synthetic training environment. So several years ago, I had the opportunity to see Major General Gervais present this concept for the next generation synthetic training environment. And she was able to articulate on stage a concept, so at a base level, that has been talked about for a long time across the DoD and intelligence communities, that is the concept of being able to train like you fight and fight like you train, right? So in the context of the training world, this has been a mantra that has never really been able to be fully realized because of a lack of digital content and geospatial content to power the training and simulation environments that are currently in use today. So for those of you who are also not familiar with that M&S side of the world, which has been a little bit tangential to this geospatial intelligence community, Today's training and simulation environments are predominantly handled in relatively small, discrete databases. A lot of the ground level simulations are done with what's called geotypical data. So they're simulations of data that look interesting and look real, but don't actually represent a real place. So this is a lot of data that's created by artists. You can think of it as your kids playing Halo at home, something similar. When you want to get to the point where you can have a virtual training environment and put people on the ground, the quality of geospatial map data at scale really just hasn't been there in the past in order to support that fidelity of an environment. So One World Terrain kind of flipped this around and threw a challenge out there and said, hey, we want to build a high-resolution, geospecific digital foundation for the entire planet that will truly enable our soldiers within the Army and the broader DoD to be able to train in the environment and inside of the same data that they are going to be fighting on in the future. And it's a pretty simple statement to throw out there, but that's a huge, huge task. So the concept of being able to get to a new reality where we're generating geospecific, so talked about geotypical before. Geotypical in the context of the M&S world means that it looks real but isn't real. Geospecific means that it actually is real, right? So this is kind of common sense for us in the GEOINT community, where we're focused on collecting real data about the real world and being able to describe the real world in a mathematical and an analytical way. So for them, they're flipping over and saying, we want a geospecific, high-resolution 3D terrain for the entire planet to enable warfighters of the future and all of those kind of next-gen digital systems that we're working on to be able to interface with this. This is the one world terrain to be able to power all of the future Army M&S initiatives and also be able to transition over into the operational side of the world. And Josh is going to talk a little bit about some of the challenges that are inherent in that context. But what this means is that she kind of threw out this challenge 2 years ago, and it popped up a bunch of questions. So number one, starting with the bare 3D terrain, we've lived in a world where SRTM overlaid with imagery has been our version of the world forever. And the reality is that as powerful as that program was 15 years ago or 20 years ago, it is not representative of the human scale world that we live in today. And so this is taking the concept of both global scale and also the scale with respect to fidelity that we're talking about. So shifting over to say that SRTM covered with imagery is a great place to start, but if I want to actually be able to accurately, including the ability to propagate errors through, accurately represent San Antonio, I need terrain data and I need 3D content that is at the human scale that we all interact with today. So I can put on my Vricon hat for a second and say that we are one of a number of players in the marketplace who've come in over the last several years, taking advantage of current capabilities in commercial supercomputing capacity, the advances that are being made with computer vision and image processing capabilities across the board, both in the academic community and in the commercial industry and in the government as well. And pulling some of the tradecraft out of our kind of geospatial and GEOINT community, bringing all these things together into really, truly scalable production capabilities. So for us, we're thinking about that kind of base foundation content, and we're going out and pulling as much high-resolution commercial satellite imagery that is available. Good news is there's a lot of commercial satellite imagery available today and a lot of remotely sensed data available today. And as our past NGA director, Robert Cardillo, used to say, we can only expect that volume of remotely sensed data to grow exponentially in the next several years. And we're kind of preparing for that scenario. But the reality is with these modern computer vision capabilities and image processing capabilities, we can start to take all of that real remotely sensed data, bring it all together, conflate it, do multi-view stereo reconstruction and generate very accurate, much higher resolution, kind of foundational terrain data that actually provides users like the Army in this context with One World Terrain with a base map that is a whole lot closer to the human scale that they're trying to get to, and actually enables you to start looking at being able to correlate and conflate other remotely sensed data sets to kind of bring you that last mile down to the street level that they want to be able to operate with. And the kind of key next step that builds on top of that, and Meida's going to talk about this in a minute, is some of the really cutting edge stuff that's starting to happen with implementations of machine learning and deep learning, as well as applications for kind of advanced image processing and spectral processing to be able to do classification, segmentation, really take kind of foundational geospatial data and be able to cut it apart into all of its parts and pieces and have a fundamental math model underneath that allows us to take data from many different sources, conflate it, correlate it together, and make it smart to the point where you can actually start generating these types of training databases and mission rehearsal databases, things that special forces have been kind of the main drivers of, and that have traditionally been very expensive and very slow for all intents and purposes. And we can start actually articulating a concept and demonstrating capability to be able to do this in an semi-automated, working towards automated way, that's going to really get us to the point where soldiers in the Army, not just the kind of special forces side of things, really can get down to training in the same environment that they may have to conduct operations in. And that's really a powerful thing, and I think my other panelists are equally as enthused about it as I am. But I'll hand it over to Meida now to talk a little bit about where things are going from a classification and segmentation side of things. I'll hand this to you.
Thanks. So I will talk about how we use machine learning under the One World Terrain project for segment the terrain data towards fully automated terrain segmentation. I will start this talk with a quick video talking about the background overview of the workflow.
One World Terrain is part of the U.S. Army's synthetic training environment, which seeks to revolutionize the way our soldiers prepare for complex threats and operations. This research is built on a 5-phase workflow that goes from the collection of data to its final application. One key advancement will be in the classification and segmentation of terrain features, which is part of the processing phase. Features like structures, vegetation, and road surfaces require special handling in a training and simulation context. For example, both trees and concrete walls can block line of sight, but trees are more easily damaged than concrete. In short, when real environments are turned into virtual environments, they don't yet have the attributes that make them useful in training and simulation. This means that terrain data needs to be rendered into classified objects, and those classified objects make up segments such as buildings, trees, or the ground. Classification and segmentation is currently a mix of supervised and unsupervised machine learning algorithms. It starts with the data, in this case, a point cloud generated with photogrammetry software from a drone collection. The user manually segments a few buildings and trees as training data for the machine to learn how, and then the segmentation algorithms extract ground, vegetation, and building features. After viewing the segmented layers, the user makes corrections as needed to the training data. If needed, roof styles and building footprints can also be extracted. Finally, 3D meshes generated earlier in the processing phase are segmented based on the point cloud segmentation. Now, these layers have the attributes needed for use in a real-time simulation. For maximum efficiency, accuracy, and usability, this process needs to become completely automated. One World Terrain researchers are working to make this a reality through state-of-the-art machine learning and computer vision algorithms. Ultimately, advances in classification and segmentation will give ground units a robust toolset for decision-making. With it, they'll be able to make real-time decisions using accurate, real-world, geospecific virtual environments at a level of interactive quality never seen before.
All right, so let's just give an overview of how we're working with the data. So we are focusing here on the photogrammetric technique. The one that I'm going to be talking about is come from the drone collects. So here shows a workflow from the photogrammetric, we get those geospecific point cloud, geospecific meshes, and the auto photos. We first identify the ground materials like paved road, dirt, grass. From the auto photo, we classify the point cloud into top-level terrain elements like ground, man-made structures, vegetations. Then we extract the object information such as building footprint, roof styles, the individual tree locations, the width, height, and we are currently looking into windows, doors, light poles, cars, those small objects. Once we have the point cloud segmented, we can segment the mesh based on the result from the point cloud segmentation. And those segmented mesh can be used for creating the virtual environment for simulations. So I will talk more into the top-level terrain element segmentation. This is our previously designed semi-automated system. The idea here is to design a bunch of handcrafted features like planarity, curvature, sphericity. We also propose 2 different features in there, including the OpenStreetMap information and the texture information from the auto photo. With those descriptors, we can train a classifier based on a manually labeled point cloud. Then use this classifier to classify the rest of the points in the point cloud. The reason that this is a semi-automated system is because when we do the data collection using drones, we may fly it with different altitude, different sunlight condition. That will result in different quality in the data. And hand-crafted features are not robust enough to transfer from one kind of quality to another kind of quality. That's why every time when a new data set comes in, we have to manually do the segmentation and teach the algorithm how to segment the rest of the data. Why we want to go from semi-automated to fully automated? Of course, everyone wants the fully automated system. We can improve the accuracy. Semi-automated systems are constrained by the workforce talent that's available, where fully automated system can be easily scaled up for larger and larger data sets. So this is our designed fully automated system. As mentioned before, the limitation from semi-automated system is that it's handcrafted features. We all know that deep learning offers amazing feature extractions. It extracts a bunch of features that are robust from one quality of data to another quality of the data. Here, the uniqueness of our design workflow compared to the existing workflow out there is we train different models for different purposes. For example, we trained a model to segment the ground versus everything else. Then for those points in the everything else category, we can train another model to just segment man-made structures from vegetation. The benefit of having 2 different models is that we can easily plug in a post-processing in between models. For example, the ground versus everything else, if there are some points floating in the air, well, you don't have points floating in the air if it's ground, right? So we can just put those points into the category of others. Once we do the man-made structures versus vegetations, we can do another post-processing, first smooth out the result. And then if you say the later application requires more accurate for building versus vegetation, you can also do a post-processing just to trade off between the accuracy of the 2 categories. The reason that I have put a quotation mark there saying it's a fully automated system is that this one can overcome the data quality, but it cannot overcome if you have a data set that built with military camps kind of data. And then now you give me a new data set that comes from Disneyland with those fancy structures. Well, the model doesn't work that way. It has to be another military camp kind of data. which lead us to this, how we can achieve this true fully automated system, which is our current and future work. The idea here is very simple. Imagine if I give you a 3D model with some shading, 3D geometry information, you'll probably, without texture, you probably understand where are the buildings and where are the trees, right? If I give you a 2D images with color but no 3D geometry information, you can also identify buildings and trees, right? This offers us that we can create two models, one based on the geometry, the other one based on the color. Now you give me a new data set. I apply both models on this new data set. It cannot achieve 90% accuracy. It probably achieve 50, 60, or 70% accuracy. But with the confidence interval, you can probably extract 10% of the point that are 100% or near 100% accurate, right? So with this 10% point, you extract it from a geometry model, you use it to fine-tune your color model. And then you probably can extract more points that more accurate from the color model. Then you fine-tune your geometry model. You see, we have those two models that they are trying to teach each other. And we believe this is how we can achieve this true fully automated system by having two models. Thanks. Yeah.
Thanks, Meida. I'm Josh Delmonico. I work at the Army Geospatial Center. I spend a lot of my time working with current Army systems, and the term current may be a little bit of a misnomer because those systems sometimes have technology that's been out of date for 5 to 10 years, still out in use today. We'll have ArcGIS 9.3 in some of our systems through 2025. So I get the enviable position of hearing and seeing all of the technology and things that are possible at conferences like this, and then there's a part of my mind that says, yeah, but we've got really old technology. In some cases, we have really bad or non-existent networks, and we're trying to field capability like this in a very difficult environment. If you're not familiar with the Army Geospatial Center, it's located in Alexandria, Virginia. It was previously called the Topographic Engineering Center. Our director is the Army's Geospatial Information Officer, Mr. Gary Bloom. We have a Warfighter Support Directorate, which really focuses on providing data to the warfighter in theater. I'll have a slide with one of their example products in a second. The System and Acquisition Support Directorate, where I work, which we do things like field a couple of different systems. We provide expertise. My team works on looking across mission command systems predominantly and figuring out how to share geospatial data, and then we have a research component that does some research work with groups in addition to One World Terrain. Some of our core competencies, I talked about a few of these a minute ago, but I have a modeling and simulation team under my branch that does a lot of work with the synthetic training environment and the One World Terrain group. I do a lot of standards work. We do a lot of work with Army acquisition programs, a lot of data modeling, really exciting stuff. Next slide. This is an example of a 3D Buckeye Collect. If you've heard of Buckeye, that's run out of our Warfighter Support Directorate. They have a 3D model of New York City that was collected last year. This is an example of some of the kinds of products that are available through the Army Geospatial Center and what will also be used in things like One World Terrain. And I'm going to talk a little bit about some of the challenges in using this data. So if you look on the left-hand side of this slide, we have a variety of places that we're going to get data. We're going to have soldiers in the field collecting data. We've got drones, things like Meida and Isaac talked about. We've got commercial data sets. We've got NGA, other governmental organization, and our allied partners. And that data comes in various standards, formats, accuracy, resolution, some raster, some vector data. And then on the far right-hand side, if you think about the One World Terrain paradigm we've talked about, we have to figure out how to take all of that data that's generally 2D data, maybe some LiDAR, maybe some elevation attributed geospatial data, and feed it into a variety of systems to include Microsoft HoloLens, to include a Samsung Galaxy Note that's had all the wireless stripped out, put it in a tank in a Humvee with various pieces of technology. So one of the big challenges is how do you take this fundamentally 2D design systems and 3D data, and how do we make those things work to meet that train as you fight paradigm that Isaac talked about. So some of the risks that we have when you think about global coverage of data that supports operations and training, that's a huge challenge, right? In order to support operations, not only do you have to have global coverage, but you have to have global coverage that's up to date enough and current enough that you feel comfortable putting soldiers on the ground to fight based on the data you have. So it's got to be, you know, in some cases less than 24 hours old, right? So if you think of all of the things that have been said so far today, there's huge technology risks. This has never been done before. It's an unprecedented size and scope of a project. A lot of unproven technology. There's still a lot of human in the loop that we're challenged with. Quantum leaps required in current capabilities, so not necessarily, there are, I think, quantum leaps required in commercial capability, but huge leaps required on the military side as far as what our systems can do currently today and what is envisioned for them to do in the future. And then we really can't do it alone. No vendor has the answer, no single government organization has the answer. We are all gonna need to work together if we have a chance at meeting this kind of a capability. Some of the capability improvements really fall across that spectrum of you know, from creation to use that Meida had in his slide from One World Terrain. So if you think in the collect, update, and manage, there are challenges from, if you collect data from a drone, how do you process that data into a 3D model? Does that data get perpetuated across the organization? Is that something that you want to take a small local drone collect, and how do you get it into a global data set and perpetuate it across for everybody to use? And do you in fact want to do that? How do you decide if data is usable or needed or appropriate to perpetuate across the organization? Also things like storing and processing, right? We talk an awful lot about the cloud, but there are barriers to implementing in the cloud, from cost to security, but we can't store all of this data globally in a 3D model in anything other than a cloud. And then how do you connect that cloud to a tactical user? Converting data to 3D from 2D, or taking 3D data and processing it into data that's available in training systems, that's a huge challenge. These guys both talked a little bit about kind of the current processes, still a lot of human in the loop. It still takes a long time to do that work. So I think we need a lot of help in how to convert and either go back and forth or support geospatial systems and modeling and simulation systems in 3D. Then there's kind of the delivery. How do you move that data from the cloud into the user's hands? How does the user system use that data? All of our mission command systems were generally built to use 2D data. We've been able to do some finesse and get some 3D data in there, but it's not necessarily georeferenced. It loses all of its attributes. So these are some of the challenges we face in implementing the kind of vision that is the Army's working towards. So how are we going to go about this? In addition to working with a vendor, academia, and other governmental organizations, we're kind of focused in my organization on looking at, in storage, look at kind of file formats and standards. How do you store that data? Can we pre-position it to minimize the amount of network traffic and just push updates? Do we utilize web cache? Can we do peer-to-peer file sharing? If we want to reduce latency, we're really looking hard at upgrading our networks through part of our modernization efforts. That's going to take some time. Minimize network dependencies, and then also potentially transmit updates and reduce file sizes. We're going to be doing some research in alternative and new compression methodologies, file sharing and streaming technologies, and then another challenge that's really large, and this is taking multi-resolution terrain data. You know, let's say you have sub-meter terrain data and then SRTM data, and they meet together. You're going to have a big cliff between those data sets if you put them in the same globe. So really figuring out how to deal with that is a huge issue. So I'm just going to hit on a couple of things that we're working on specifically. One of the challenges is the 3D data model format generally used today is OBJ. One of the big challenges with the OBJ, or a couple of them, are that it does not natively support being georeferenced, and also you can't store attribute data in there. And that makes it a really big challenge if you want to use these 3D models in operational systems, because that's one of the major things that operational systems require. So my team will be working with industry, with this synthetic training environment, CFT, and the Open Geospatial Consortium over the next year or two to look at what's the right file format and standard for OBJ files or the next generation of file formats to handle those two problems. This is a slide I spend a lot of my life in, so I'm sorry about that on a Sunday morning. This really shows how the Army's going to focus on standards and reducing the number of standards over time from left to right, going from more standards to less so that we can focus on interoperability with a few standards across mission command systems. We're looking at adding OBJ potentially in the future, focused on maybe GeoPackage is one of the things that we're really pushing, and maybe we can look at OBJ, 3D models inside of a GeoPackage. We're doing some current work with things like vector tiles, portrayal, a routing API, and a couple of other exciting things with OGC right now that you'll see coming out in the next year. So by working on kind of those standards, that's going to enable us to solve some of the problems that we're looking at. I'm pretty sure that's my last slide. Yep.
All right, thank you, everyone. Before I begin questioning from the number of questions we got in, I want to remind you that you have the opportunity to join the conversation. Besides the cards going around, please text any questions. Text the word GEOINT to 313131, and that will provide a card that we can bring up and add to the conversation. As a starting point, I had a very interesting question come up already. When you think about segmentation, and this is, I think it was addressed at Meida, but I think it actually applies to all of you in a sense. The human terrain elements of the segmentation process. How do you gather those points and how do they fit in? So beyond the physical features of the thing, how do you bring that into your augmentation process?
You can start and I get to jump in. How about that?
So for the segmentation, it's really how the model is actually learning from those features. It's basically what you told the model to learn, and the model has the capability of extracting the feature that it needs. It's not really like you are teaching the model. You're basically just creating algorithm to do that work for you, and we are just trying to make this model can self-learn instead of we teach it. Right?
Yeah. So I'll add to that, because this is a challenge that we've been working to address for some of our commercial customers, actually, in the telecom world. So it turns out that being able to classify buildings and vegetation is very important for doing radio frequency propagation modeling, but also being able to classify what's a hospital, what's a meeting event, or what's a venue where people gather, what are the population dynamics that go along with these things are kind of important when you're trying to model out how much bandwidth do you need to vector to a specific location. And so I'm going to step back and give kind of a broader answer that highlights the fact that one of the really powerful things about using a deep learning or machine learning type approach to address some of these problems is that you're not constrained to any given single input into your models. And so this is where, on Meida's last slide, he was showing you kind of the approach in a fully automated sense to be able to have kind of parallel pipelines that are working in image space and 3D space and being able to have them train against each other. Well, Barry and I have some old history in sandy places dealing with some of the fun things that happened with the explosion of multispectral and hyperspectral image science over the last 10 years. And if you start thinking in a geospatial context about multiple input sources that are well correlated together and being able to leverage all of these different types of input sources as inputs into your machine learning models or your deep learning models, your ability to characterize attributes expands enormously. So from the image science side of the world, one of early applications of hyperspectral image science was looking at material characterization, right? Can we identify a specific chemical compound? Can we identify blue tarps, et cetera, right? So if you start thinking about, well, what happens if I can take spectral characteristics with traditional kind of RGB image characteristics and add 3D geometry, and what if I push all those into a deep learning model and apply and build some neural nets around it? What kind of information can you build out of it? And the cool part is you can build these training sets that say, I'm looking for these things, and I can manually tag these things, and the deep learning models get to take all of these different inputs and apply them in ways that we may not necessarily understand, and come out with a model that we can characterize how well it will generate the results. Even down to those types of really kind of complex attribute questions, right?
Thank you. I've gotten a question in about 4 different formats here, so there's obviously some serious interest in this community with this. Thinking in terms of GEOINT tradecraft, as we start to automate these large activities and do automated segmentation and change the role that the humans play in data development, the question is, are we thinking about the new types of functional tradecraft that the community would have to have? What training goes into those things, and where are the career paths going forward in this new environment?
That's a fascinating question.
Anybody want to take a cut?
I can start, but you guys. So on the industry side of things, absolutely. And it's a pretty broad question, right? So yes, tradecraft will change with different tools. Understanding the tools and how to employ them will change the way that we employ tradecraft throughout the community, right? And it's going to open up some opportunities for new tradecraft requirements that we don't even, or that we have not really had to think about thus far. I had the opportunity to sit on another AI and machine learning panel with the director of analysis, Sue Calwitt from NGA, and we got into a discussion about some of the sensitivities with respect to current deep learning and machine learning technologies with respect to verification and validation, right? So how sensitive are some of these models to exterior influence that we may or may not be able to understand? And that's something that is very challenging for a community like ours in the GEOINT community, where the accuracy of the results and the quality of the results are very, very important. And this kind of gets back to Josh's point of this is a big, huge problem set when you want to try to connect operations into the training side of the world, because as you guys all know, the accuracy side of things is really important. And when you start introducing models that are coming up with answers that you don't really understand how those answers are being generated, but you can prove them empirically in most cases, and you start applying them to denied environments around the world where we don't have a lot of truth data, what kind of influences do we have to watch out for from potential bad actors influencing the source content going into those models? And how do we understand them? How do we protect against them? And how do we change our mindset with respect to verification and validation in order to think about kind of quantitative statistical mechanisms for doing verification and validation that can help identify some of these things ahead of time? I think those are all places where we're going to have to develop some new tradecraft as a community. There's a lot of, I think there's a lot of opportunity to collaborate with industry, academia, and the government in that context, because everybody has different kind of stakeholder positions in there.
And I think that all of the things we've heard about today, quantum computing, AI, ML, 3D, all of those are things that are going to continue to grow in the GEOINT space. So I think anything that you hear about at this conference will be a place you could invest potentially your entire career in, particularly over the next 10 or 20 years.
So an interesting question here that sort of struck home for what I spend most of my time thinking about this on is that as we move into the geospecific solution, the smaller, more high-resolution objects that exist in a scene are perfectly modelable at a localized environment using the drones, but I actually have a specific question. What do you do when you're trying to move into mission space where there's denied areas involved, and what is the best methodology to allow exploitation in that realm? And I know Isaac's going to have something to say on that because he spends a lot of nights not sleeping trying to figure that exact problem out, so I'll start with it. But I'd like to understand the Army's application of that also.
Why don't you start, Josh?
Yeah.
All right, so I think the Marines and the Army are doing some things today with drone technology, and I mean that's probably part of how we'll collect some of that data. Some of it will be air and satellite-based data collection. I mean, it's not where I spend my day job, so I don't know that I have a lot more to add than that, but I think that's probably, hardening those capabilities and collecting data, unit and soldier-based data collection at a highly localized level is probably where that'll happen.
Yeah. So as Barry said, I think about this a lot. So my general response to this question comes down to the fact that we, at a systems level, and as we're discussing this type of capability, we need to think about collection in ways that are different than we have in the past. So in the past, exquisite collection was something that we tasked, right? This has been a strength and a competitive advantage for the United States and for our community for a long time, is our ability to go out and collect things in places, denied places around the world, in order to support our mission objectives. The incredible advances that have been made in commercial remote sensing technology over the last 2 decades have changed that paradigm a little bit, and have opened up a whole bunch of new opportunities to be able to exploit exploit commercial collection or open collection in ways to generate data that is, in some cases, more exquisite than we could have possibly imagined previously, but with different challenges. So in a world where I can take a better, higher resolution image on my phone and post it to Instagram in 8 seconds of any place that I happen to be visiting, than anything that I could get from an airborne ISR asset flying over that location, it's incorrect to think that that data that's being collected and just posted into the open source world is not valuable. We have to think about how we correlate that data into kind of our mathematical model of the world. And that's a huge challenge, and it's one of the big open challenges that One World Terrain is ultimately going to have to address. So correlation, the verification, validation, how do we understand where it's coming from, what's the provenance, all those sorts of things that, that this community has been dealing with VGI and some of the other open geospatial data initiatives that are out there, can be applied in the same context. So in places where people are, I mean, it's amazing. You can go on YouTube and you can literally find dash cam footage of a 360-degree camera driving around the streets of Pyongyang on YouTube. Better, higher resolution than what you'll probably get from just about anything. And it was some Russian guy in a truck driving around in a car. And so the real challenge that we have now is how do we figure out, and this comes back to the how do we correlate data from at different quality levels and from different sources, but being able to leverage that data is how we're going to overcome that problem set, right?
Thank you. So we're just about out of time. I'd like to summarize quickly that this is actually a longer conversation. The community here is getting into a realm where we're in a transformation between traditional tradecraft with folks sitting in individual workstations and compositing their work into reports and moving it out to one where we're interacting with the environment. The Army's training step is just a first step into a larger world where these interactions occur as a community conversation between the online world and the real world. Scale and automation are very important to this whole thing. Figuring out ways to do advanced segmentation to features that we haven't considered or do not translate easily into GEOINT but are critical to the community moving forward is very important. And moving from the modeling cultures that were evolved for very different processes to something that allows for the sort of conflation modeling additions that are going to have is critical. So I invite all of you to seek out the speakers here and in the future. Reach out with your ideas, because there's a lot to be done as a community collaboration that hasn't happened yet, and we want that to. And I'd like to thank you all for your interest today. That's it.